Okay, any questions? No questions? So like I said last time, please ask me questions on Slack. Otherwise, if I don't hear any questions from any of you, I will assume that everything is very easy and I will start asking questions. It's a good time to
So,
ask.
like we would request you to like put that deadline after the spring break, so
Say,
we'll catch up and ask question during the spring break.
yeah, of course. It's not that we are going anywhere, right? We are all gonna be on our computers anyway all the time. Anyway, you can ask questions anytime. Normally, I won't answer questions on the weekend, but during spring break, I will be fine. Great. So, what have we been talking about? We have been talking about black body radiation, or another way of thinking of it is gas of photons. And here we said that we cannot really control the number of photons we have. So grand canonical is not a good idea. Let's look at canonical. And even there, let's not worry about the number n. So we looked at Q as a function of Vt, which is strange at first glance as to why did n go, but it's just that we are not varying it. We are not even considering it. It's out of the picture. It cannot be controlled. So that we wrote down as nu over e to the power minus beta e nu. And the e nu here was coming from looking at every microstate n1, n2, nj dot dot dot, and then doing e to the power minus beta, n1 epsilon 1 plus n2 epsilon 2 plus dot 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 plus nj epsilon j plus dot dot dot. So before you get lost here, this means this corresponds to energy epsilon 1 given by h cut omega 1. This corresponds to energy epsilon, and all of this goes from 0 to infinity. Jth one corresponds to epsilon j correspond to omega. So we are assuming that there are frequencies that the system can take, and there will be a certain distribution of frequencies, just like we had in the phonon case. Phonon case, we had a distribution of frequencies where famously Einstein said that the distribution of frequency is just omega minus omega Einstein, delta function 3n. And Debye said that it goes up till here like omega square and then cuts off at omega d, right? This was for phonons. Similarly, for photons, we will also think about the density of states. Sometimes in previous years, I have actually derived the density of states for photon. I will tell you how to derive it, but I will just show you the expression. So we have to think about the density of state for photons. Same thing, g of omega omega. That will matter. But right now, let's not get into what exactly is g of omega. But g of omega tells you is what is basically the probability of finding frequencies at this value over here versus probabilities of finding frequencies at this values with the blue over here. You can see that it's more likely to find probabilities with blue frequency. And if you have a frequency over here, the probability of finding it is 0. That was what we saw in phonon. So similarly here, we need a probability distribution. But once we have such a probability, then we have a harmonic oscillator, quantum harmonic oscillator, which can exist in different states. It can exist in ground state, first excited state, second excited state. So ground state energy is half h cut omega j for that one. Then 3 by 2 h cut omega j, and so on and so forth until nth state is n plus half h cut omega j. In this expression, we ignore the 0 point energy because it's just a prefactor that comes out here, right? So we ignore that part. So we set ahead with this, and then what did we do? We said, okay, well, at 0 temperature, everything would like to be in the ground state. So at 0 temperature, the average occupation number of the frequency J is going to be 0, right? At 0 temperature, because, well, everything will just be in the ground state. There is no excitation. But at higher temperatures, as you increase the temperature, they will start to populate the excited states also. So this thing will be definitely more than 0 at positive temperature, at non-zero temperature. So we wanted to calculate what will that value be. And that's what we did. We calculated our average value of Nj. In order to do that, we went to every microstate, N1, N2, Nj equal to 0 to infinity, Nj e to the power minus beta, N1 epsilon 1 plus everything divided by Q. And this turned out to be partial ln Q by partial minus beta epsilon j. We had calculated Q explicitly for this system by converting this into a product, if you remember. And from that, we got that average Nj is equal to 1 over e to the power beta epsilon j minus 1. And this is called Planck's distribution. So this tells us if you set beta is equal to infinity or temperature is equal to 0, then e to the power beta epsilon j tends to infinity irrespective of the value of omega j, and nj tends to be 0, right? You recover what you thought will happen at a low, as temperature tends to 0. And at a finite temperature, it tells you that the thing goes to higher and higher energy levels. As beta goes down from infinity or temperature goes up, the value of Nj increases. So this is Planck distribution, which is all well and good. Let's call this equation number 1 is this. Let's call this as equation number 2. The question now is, the problem that we really wanted to answer is, what is the average energy per volume over any frequency? This is what we wanted to calculate. This is what we want to calculate. So we have this black body radiation where we know photons are being created, destroyed, whatever, all kinds of funky things are happening. And we want to calculate the density, the energy of this system. We know that's going to be extensive. So let's divide it by volume. So it will be intensive. And we want to see how it turns out. Anyone recall from high school physics, how does this thing depend on temperature?
T to the fourth.
Yes, exactly. So today what we are going to show that it varies with t to the power 4. And in fact, with a very high accuracy, we can derive the prefactors, which are beautiful because all these constants that you have ever seen, they come up together. And this thing is actually quite accurate. You have speed of light, you have pi, you have Boltzmann constant, you have Planck's constant. It's like, how on earth did all these constants get together? So this is called Stefan Boltzmann law. And I'm not going to worry too much about the prefactor, although I will show you where exactly the prefactor comes from. And online, I have posted a PDF which goes through the full detail and gets everything, the prefactor light, right, and everything. This is what we are going to derive. So in order to do this, this is over any frequency, okay? So this thing, U by V, is going to every frequency. Frequencies can go from 0 to infinity, d omega, and looking at the energy density of that frequency. This is energy density per volume of frequency omega, right? So that's what we need to calculate. We need to calculate U of omega, which is what is the average energy. Let's call this equation 3. Average energy, I didn't number the Stefan Boltzmann law because we are going to derive that. So this is what's going to come up. We will now show. This is what we are going to show. So average energy per volume at frequency omega. That's what we need to calculate. Okay, how do we do this? In order to do this, we have to think about, first of all, we have a per volume, right? So let's divide by 1 over volume. Then we have to think about how many oscillators do we have with that frequency? Well, that is the density of states, right? G of omega. Then we have to think about what is the energy on an average associated with that oscillator. That will be given by n plus half h cut omega. Is this correct, or did I make some mistake here? Do I need to change something in this equation that I wrote? In equation 4, your hint is I'm talking about average energy. So what should I change, or is this correct? We have to make this as average, right? We have to talk about average value of n at that frequency. So this thing is going to be 1 over v g of omega, and I'm going to ignore 0 point energy again because it's just a prefactor that turns out that doesn't really matter. Average n multiplied by h cut omega. Okay, that's what we have. So
just clarifying. So this average n can then, I'm guessing that now you get this because you're sort of looking at these fluctuations between energy levels, and so that n can now be
in equation 2.
Oh yeah.
We just derived it, so we are all set.
Correct. Yeah. Okay.
We are all set. So that average n is Planck's distribution. That's exactly Planck's. That's exactly what we needed. So this is Planck's distribution, and we just showed that this thing is. So we have this h cut omega. Let's keep this here. H cut omega divided by e to the power beta h cut omega minus 1. The question still remains of what is g of omega. So the g of omega for photons can be derived. In the previous years, I have actually derived it, but it gets into quantum mechanics, and I don't want to go too much into it. I have posted the PDF online. You can go and look at it. The key idea is you think about the number of ways in which light can be polarized. You take that into account. You use the particle in a box solution from quantum mechanics. And what you will see is that, so particle in a box, which is the first thing you learn in quantum mechanics, using particle in a box, and see extra PDF online. Okay, so I'm not going to derive g of omega in this. In the perspective we are taking in StatMech is that g of omega comes from some other theory, density functional theory calculations, spectroscopy experiments. It's not our business in StatMech to go and calculate g of omega. Okay, when Debye did g of omega, he got it from theory of solids. You might be getting g of omega from neutron scattering. I'm not going to talk about it, but it's an input that I get from somewhere else. So u of omega is equal to this thing. Let's call this equation 5. So there you will see that g of omega is actually v omega square by pi square c cube. It's remarkably similar to the Debye expression, which also I introduced. The Debye expression was 3v omega square by 2 pi square cs cube. So the Debye expression have speed of sound. Here you have speed of light. Okay, and you don't have a 3, you don't have a 2, but otherwise it's really similar. There is one difference. In Debye, and that's the physical thing that we talked about. In Debye, we said this is true if omega is less than a cutoff, because we knew that we are talking about vibrations of atoms, right? So it does not mean to talk about vibrations which have a higher frequency. Very high frequency means very short wavelength, right? So if you make the vibrations very, very high frequency, you come to a wavelength which is comparable to the interatomic distance or the bond length. So we had a sharp cutoff there. For photons, we don't have such a cutoff. For photons, this is true for all omega. In fact, the density of states of photons just diverges with the frequency. You can have more and more. There is no cutoff. And for those of you who have done particle in a box will remember this, will see intuition for this. When we do particle in the box, we talk about the wave numbers or the wave vectors, right? We have this quantization. Do you say that stop the quantization at a certain value? No, it keeps going on and on and on. So there is no limit. There is no cutoff over here. It's just like this. So you would think, wait, is the energy going to diverge then? So let's call this as equation number 6. So let me write it down once again. So equation 5 says U of omega is equal to 1 over volume and G of omega multiplied by h cut omega by e to the power beta h cut omega minus 1, right? So we had 1 over volume, the density of state, the energy, and average number, right? Equation 6 says G of omega is equal to volume by pi square c cube omega square. So this diverges with omega, right? And we need to put 5 and 6 in equation number 3, where we are going to integrate it from 0 to infinity to get u, capital U over v. So this diverges, but the thing is this also goes to infinity, right? The denominator also goes to infinity, and the numerator diverges as omega square, but the denominator diverges as exponential. So in fact, if you look at this plot, u of omega versus omega, it's going to look something like that. Depends on g of omega. When omega is small, it goes up as omega square, right? You can imagine that. When omega is square, you can use the L'Hopital rule and see that this thing, the h cut omega by e to the power beta h cut omega minus 1, limit is 1. This thing goes as omega square, but at some point it starts to go down. And then it behaves as e to the power minus omega. This is Planck's. So with this, we have our final formula. Actually, let's write it down. So mix 5 and 6, equation 5 and 6, to get u of omega is equal to h cut omega cube by pi square c cube e to the power beta h cut omega minus 1. This formula is kick-ass. It's super, super powerful. We just derived it by scratch. The only thing I kind of threw at you is the value of this proportionality constant, right? But the omega squared dependence you were already familiar with. You had seen it in phonons, and you can appreciate physically the concept that why does it not have a cutoff. But with this, you get an expression. And again, deriving this g of omega, which we use here, is actually 1 page of algebra. It's not too hard. If you go through the notes, if you have done quantum mechanics, it's really easy. It's really, really easy. You derived all of this from scratch. Let's call this equation number 7. This formula is called Planck's formula for black body spectrum or spectra. This is super powerful. This can fit things so accurately, it's kind of mind-boggling. So some of you might have read this story about 2 scientists called Penzias and Wilson at Bell Labs around 1950s or 1960s. So they were trying to study the early universe. So they made a telescope, which was super cool, super big. And they worked and worked and worked on it, kind of like many of you in grad school will work on some instrument for 4 or 5 years, or hopefully not more than 4 years. And then in your 5th year, you will make some measurements on it, right? And then they were like, okay, now we have made this very good instrument, but there is always background noise. We can't seem to get rid of this background noise. It just never goes away. They became quite frustrated. So they went around cleaning the thing. They cleaned it in every possible way. In fact, they had a bunch of pigeons in the area who would go and take a shit on the telescope all the time. So they kept around scraping the pigeon shit everywhere, and still it wouldn't go away. And then they realized that was the radiation from the early universe that was making that sound. And they were able to fit it basically using this formula in some related form and recover the early universe temperature. And this was then became a part of the COBE experiment. And in the PDF that I have posted online, they talk about this experiment in like this equation in awe, because it fits the early universe frequency in like 10th decimal digit accuracy. It's so accurate. So it's a fantastic equation, which we just derived. Now we can use equation 7 in equation 3, right? And get our u by v. What was that? That was 0 to infinity d of omega u of omega, and we have everything, right? So it's going to be h cut pi square by c cube integral 0 to infinity d of omega, omega cube by e to the power beta h cut omega minus 1. We have seen integrals like this. If you called x is equal to beta h cut omega, this becomes h cut by pi square c cube 1 over beta h cut to the power 4 0 to infinity dx x cubed by e to the power x minus 1. And again, one of those integrals that bizarrely relates to pi comes out. This is the type of stuff mathematicians like Ramanujan used to do, and it shows up here. This thing can be shown to be exactly equal to pi to the power 4 by 15. So with this, we get our Stefan-Boltzmann law. U by V is equal to pi square Boltzmann constant to the power 4, 15, h cut cube, c cube to the power t4. This is amazingly accurate. And this is equation number 8, or Stefan-Boltzmann law. So I did a bit of cheating in deriving Stefan-Boltzmann law. The key cheating that I did was I just told you what is g of omega. I told you that g of omega is, so this I can call as cheating, quote unquote, because I did not derive it. Look at PDF, it's derived. If you understand that, then you will be like, wow, I just derived all of this completely from scratch, just pen and paper with my superior knowledge of statistical mechanics and my semi-superior knowledge of quantum mechanics. I was able to derive this, which I think is amazing. And that's really the whole point of doing statistical mechanics, to show you how it can explain observations in nature. And I don't want to distinguish between chemistry, biology, physics. It's all a part of nature. You know, I do biophysics. Dorothy Beckett, who was in our department, used to teach a class called biophysical chemistry. You know, everything is related to each other, but you can see how powerful it is. So far we have seen phonons, where we derived the T cube heat capacity pretty much by scratch by using our statistical mechanics knowledge. And now we derived photons, a gas of photons, and their property, what is the energy density. So these are the 2 applications we have done so far. And now we are ready to move on to the 3rd application. Any questions about this? So read that PDF. It will be useful. It's nicely written. Yeah, any questions? So read PDF posted online on black body radiation. It's quite long and detailed, but it's worth reading. Okay, so we have done 2 applications so far of StatMech. We have looked at application 1, which is phonon gas. We have looked at application 2, which is photon gas. In both of them, there was a similarity, that we essentially looked at things called quasi-particles. They were kind of not really real. Have you held a photon in a hand? Well, in some sense, I am holding it, right? Have you held a phonon in a hand? Well, my hand is made up of phonons. It's vibrating, but they're still quasi-particles. You can add, you can create or destroy as many of them as you can. And that's why we did not use grand canonical ensemble, and we didn't really worry about n. You know, in phonon, it's a bit complicated. In photon, you really saw that if you can, the n1, n2, n3, nj indices ran as many as you wish. So quasi-particles can be created or destroyed with no cost, at no cost. In other words, their mu is equal to 0. Now in application 3, traditionally in StatMech books, they start with application 3, but it's actually more abstract. I like application 1 and 2, so I start with them because they lead to something like Stefan-Boltzmann law, which many of us have seen in first year chemistry, first year physics, or even high school. And now you go and derive all this, which is kind of fun. So now we are going to look at quantum statistics of particles, not quasi-particles, but actual particles. So these cannot be just created or destroyed. We will have a constant number of particles. We can enforce that. Furthermore, these particles can be bosons, or these particles can be fermions. And I will I introduced this term in the in a few lectures ago. I did not talk about it too much, but now we will talk a lot about it. Bosons follow what is called Bose-Einstein statistics, and fermions follow what is called Fermi-Dirac statistics. Okay, so so the idea is that let's since we have an n, let's talk about the canonical partition function Q of n v beta nvt. You might hear some barking. Pakoda really doesn't like skateboarders, so he just saw a skateboarder go, so he's very alert. Hey, it's okay, relax. The other day he met one of you, he met Smithran, and instead of saying hello to him, he saw a skateboarder, so he came across as very angry, and he's not really angry. So let's write this down. So here we are going to think about occupation numbers, N1, N2, Nj. And again, they can be as many of them as you wish. They can start from 0. There is a difference. They cannot go up to infinity because we are forcing n number of particles, right? So the occupation number can be 0 in any of them. They can start, so you have different energy levels. You have different oscillators, and you can have one particle here. Maybe in this oscillator, you have particles in the second energy level, so on and so forth. So in this case, N1 is equal to 0, N2 is equal to 2, things like that, dot, dot, dot. And you can have as many oscillators as you wish. They cannot go beyond infinite, beyond n, because you have a maximum of n number of particles. One more thing, they must sum up to n, right? Because we have a finite number of particles. So you can see it's starting to get complicated. Summing something like this is going to be a horrible problem. So already maybe canonical partition function looks like it's not the right way to proceed. So I gave you a lot of time with homework 3. Most likely most of you did not start with it, but now is a good time to start thinking about it. That any problem there, should you do it canonical? Should you do it grand canonical? When you start setting up a problem, it will become clear that maybe this looks too complicated. I shouldn't do it. So, but in canonical, let's see how it look like. We will have energy, we will have minus beta. And then if again, ignoring 0 point energy, we will still use we don't really have to think about it as quantum oscillator. We can say that this will be given. Do we have to think about? Okay, let's just write it. This will be N1 epsilon 1 plus N2 epsilon 2 So actually, let me change this picture that I drew on the left and just simplify a life. So we are talking about energy levels that exist. Yeah, we don't have to think about harmonic oscillator over here. We are thinking about energy level epsilon 1, energy level epsilon 2, energy level epsilon 3, so on and so forth. And we have N1 particles in energy level epsilon 1, N2 particle in energy level epsilon 2, and 3 particle in energy level epsilon 3, okay? Dot, dot, dot. And we can have as many energy levels as we have. However, the number of particles in any of these energy level, if you add them all up, they must be total equal to the number of particles. And if you have N1 particles in epsilon 1, that leads to energy N1 epsilon 1, right? If you have N2 particles in epsilon 2, you have energy leading to N2 epsilon 2. And the energy levels do not talk to each other. The energy level themselves are independent. So this is our canonical partition function for this problem. This looks hard. This is a tricky combination problem. You cannot really separate things out, right? Normally, what was our tool? We would have something like this. We would think about it as, let's take this and change it to some sort of product where we are thinking about e to the power minus beta and epsilon 1 in some way, right? We can't do this over here. Do you see why? We can't do this due to this thing. We cannot factor it into a product of independent partition functions. Why? Because their sum is constrained. This constraint makes life in QNV beta or canonical ensemble terrible. It doesn't help us. So a better way to look at this problem is to use the grand canonical ensemble, and that's what we will do next. So let's try. I mean, I am telling you that it will be better, but maybe some of you see why it will be better, but otherwise it will become clear in a moment as to why it is better. In grand canonical ensemble, we will write our Z, which is going to be mu V beta. And what is the formula for Z? Anytime we can set it up for this problem, but first just write down what we know about it. Go into every microstate, calculating e to the power minus beta, E nu minus mu N nu. Okay. What is new? Microstate is the same. And when I spoke about particles taking energy levels, and I wrote down this formula for the canonical partition function, does this assume anything about the particles being distinguishable or indistinguishable? Is that clear to people? Or does it matter?
Can you ask that question again? I just lost it there.
So
Yeah.
actually, for this formula that I wrote down here,
Yeah.
should particles be distinguishable or indistinguishable, or it does not matter?
It should not matter, right? Because like their numbers matter, how many they are on energy level, but like that's all it should matter, not like their individual property.
So keep this in mind. I'm going to set this up as indistinguishable, even though as Kishler pointed out, so far it looks like it doesn't matter, okay? Since it doesn't matter what I take, right? So I'm going to set it up as indistinguishable particles. Later, we are going to look at classical properties of the system. There it will start to matter. So for now, let's just hold on with indistinguishable particles. Okay? Great. Thanks, Vijay. So let's write down the microstate over here. Microstate is the same as talking about N1, N2, Nj, all their values. They can go from 0 to whatever. And then looking at e to the power minus beta E nu for a given set of values N1, N2, Nj, E nu is summation Nj epsilon j, right? That's how it defined our energy. So this E nu over here can be written as summation j Nj epsilon j minus mu. Can we write down N nu in a similar form? Can we write down N nu as a summation over something? Emma, what do you think?
Sum of all the particles.
Yes, Emma is absolutely correct. Emma is paying attention. Wonderful. Thanks, Emma. It's even simpler, right? So maybe I should have started with that one. This is summation Nj, right? So it looks complicated, but life will simply, I mean, it's only in StatMech really that you see summation of exponential to the power summation, and it looks terrible, but it simplifies out. So if you had just written this and written the canonical, you might be like, oh, maybe this is simpler, but actually this will turn out to be simpler. So let's take this and write it again as N1, N2, Nj, exp of minus beta summation j epsilon j minus mu nj. Okay, let's look at it carefully before. So I have taken this one and written it as this thing. Okay, so this is, you can see, is epsilon j nj minus mu nj. And the summation has been brought outside. So there were two summations, both of them were going over j, right? So I just compressed it. What can we do now? Well, again, what I call as my second favorite trick in StatMax. So the first one is differentiating with respect to partition function works wonders. The second one is if you have summation of exponential, it can be changed into product of summation. That's what we're going to use here. The third one is sum of the geometric series, and that will also show up in the next step. So use second, and I cannot guarantee that next time these tricks show up, my numbering of tricks will be the same, but you know what I mean. So this is the same as taking this j and bringing it out. And I want you to practice this trick many, many times. Every time I see it, I still get like, wait, is this really correct? Is this intuitive to me? It takes a lot of practice for this to become second nature. But as a StatMax student, it should definitely be that way. So, and the sum goes inside. And now we are summing our nj going from 0 to infinity. And I'm going to ask you a question just in a bit, or if I don't, then you should be asking me that question. E to the power minus beta epsilon j minus mu nj. So what question should you be asking me at this point? What did I try to sneak in cleverly here?
Why is it infinity instead of
Yeah, there we go, Emma. Now Emma will also answer it for me. Why is it infinity? It's subtle, but it's important. You can do it. Tell me. Which ensemble are we working in?
So the grand canonical?
In canonical, we had forced the number to be n. In grand canonical, we have forced the chemical potential to be mu. So the number can vary to infinity. It's just that you will pay a penalty for it. And that's why this is wonderful. If we were not able to sneak that in, we would have the same problem, right? We would have a finite sum and things would be kind of complicated. And the reason we can do this is because we are in grand canonical ensemble. If we were in canonical ensemble, we wouldn't have done this. In grand canonical ensemble, it's just like talking about microcanonical. In microcanonical, your energy is fixed. But anytime you go to canonical, your energy can take any value. It's just that you will have a penalty due to the Boltzmann factor. Here you have a similar penalty for the number due to the chemical potential and things like that. So it will have to adjust, but otherwise this can go to infinity. So this is important. And now we can use my third favorite trick in StatMax, which is the sum of the exponentials of the geometric series. This is again 1 plus x squared. So the whole thing becomes product over j of 1 divided by 1 minus e to the power beta mu minus epsilon j. This is my grand canonical partition function equation number 10 for bosons. If we had fermions, then this double star that I did over here wouldn't go up to infinity, it would go up to 1, right? Because for bosons, nj can be 0, 1, 2, 3, infinity in equation, let's actually call it equation number 11. And let's call it equation number 10. For fermions, nj is equal to 0, 1 in equation 10. And so let's do that. Let's derive it for fermions also while we are at it. So for fermions, our z will be again product or j, but this time instead of summing a geometric series, we are just going to have two terms where nj is 0 to 1, e to the power minus beta epsilon j minus mu nj, and that becomes product over j When nj is equal to 0, this is 1. And when nj is equal to 1, this is going to be e to the power minus beta epsilon j minus mu, right? So this we can write down as product over j we will just leave it as it is. So we just derived the this was the grand canonical partition function for bosons when we allowed this to go over from 0 to infinity. And in this one, we allowed it to go from only 0 to 1. So these are fermions, things like electrons. No two of them like to be in the same quantum number. Only one of them can have the exact same quantum number. That's due to the exclusion principle. Why can't we have particles in the middle? We can, in fact, there are all sorts of funky particles with their funky statistics. We are not going to get into that. You can go and look at anyons and quantum Hall effect and this and that. The world is funky out there. We are going to only think about these two. Okay, and this is equation number 12. So we just derived Z, the grand canonical partition function for bosons, and now we derived it for fermions using the same thing. We are not quite done yet. We also need to think about the average occupation number, right? That's the thing we can play with this, right? So first of all, the first thing we can play with is, okay, as we increase the temperature, what is the average value of N that we are going to have? In what is the average N1, what is the average N2, questions like this. So let's try to answer that.
Can I quickly confirm what J means? What the index J? Like, is it the energy states or is it like?
J is the energy state. I will write down here. Nj, epsilon J, okay?
Okay, thanks.
No problem. These are confusing, always confirm with me. Yeah, go ahead.
May I have a question? So about why it is reasonable that we can sum up to infinity? Because you are using the particles, right? Which means that you cannot create or destroy it with no cost.
Very, very good question. So we cannot create or destroy it without a cost. We can create or destroy with a cost. So let me give you an example. If you are in outer space, you could move everywhere, right? Without a cost, right? You are just drifting, floating, there is no cost. If you are in a gravitational field, you cannot just go up. But if you're willing to put in the cost, you can, right? That's how rockets work. It's the same situation here. You can go as high as possible. You can escape Earth's gravitational field. It's just that there will be a cost. So there is nothing stopping you from allowing it to go to infinity. It's just that the cost comes from you. So that's why we can do that. So as you will see in the next thing that I'm going to derive, that the average Nj will still be finite. And in your homework or in your midterm, I will have you derive the fluctuation from average Nj and things like that. And we will see how it is, how it depends on temperature. Okay, so this is, and I will emphasize this once again, there is a cost to increase this, but we are in grand canonical, so this can vary essentially without any bound. There is nothing stopping it from varying. Again, think about it. The best way to think, if this still confuses you, think about canonical ensemble. In a canonical ensemble, there is an average energy, right? But if I ask you, I mean, this is the type of question I would have given as a pop quiz in class. What is the maximum energy the system can have in a canonical ensemble? What's the answer, Z?
No maximum energy.
Same idea here. No maximum number. Okay?
Okay.
It's just that the probability will be very low, but there is nothing stopping it. Okay, great. So let's calculate. Yeah, these are very good questions. I'm glad you all are asking this. And again, go back and look at it. And spring break is a perfect time. You have all learned a lot to let it sink in. I won't make the midterm very hard. It will be like my objective with the midterm is to help you put all of this in perspective on your own and just make the midterm is gonna help you understand. It won't be easy. but it won't be hard either. It will just help you understand. So go through your notes and everything, and I will give details of the midterm a week before the midterm is out. So you will have questions to ask me if you have anything. Yeah, but we are still far from midterm, so don't worry. So let's talk about average NJ in bosons, where this thing is allowed to go up to infinity. What is the average number then? So in order to calculate the average number, we have to go to every microstate, look at the value of NJ in that microstate, e to the power minus beta, E nu minus mu n nu divided by z, right? This is the grand canonical partition function. And we have seen this. We have derived a formula for this when we did grand canonical. We don't need to re-derive things again. This we know is partial ln z by partial minus beta epsilon g, right? We derived this when we did grand canonical. So now you can go to equation 11 and differentiate it with respect to e to the power, differentiate it with respect to minus beta epsilon j. So using equation 11, this becomes 1 over e to the power beta epsilon j minus mu minus 1. So we have just shown that average NJ for Bose-Einstein, which I will or bosons, but I will call it as average NJ for BE Bose-Einstein, is 1 over e to the power beta epsilon j minus mu minus 1. Now, this is a very interesting equation because we have seen something like this before. Where did we see this equation? Something similar, not exactly the same. Jessica is very silent. Jessica, I need your help. Where have we seen such an equation, Jessica?
From like the sum of an infinite progression?
No, this type of thing, 1 by e to the power beta something minus 1. Have we seen it before?
We derived it just now from the z partition function
Yeah,
itself.
but before that.
Oh, right here actually. The
We had
average.
equation 2. So
Yes.
that was Planck's distribution. But do you see there is a difference between Planck's distribution, equation 2, and equation 13? And I still have it, don't go away. Equation 13 looks like equation 2, but with one difference. Do you see what's the difference between equation 13 and equation 2?
Yeah, so since we're using the grand canonical, we also have mu.
Yeah. So how would you go from 13 to 2?
There is a factor of e beta mu.
So we set mu equal to 0, right?
0.
If you set mu is equal to 0, the 13 becomes 2. Thanks, Jessica. You can relax now. So what I'm trying to show here is phonons are bosons with chemical potential 0. So we just derived this general Bose-Einstein statistics, and if we set mu is equal to 0 in this, we recover Planck's distribution, and this is quite interesting. That's the first interesting thing about this equation. There is yet another interesting thing about this equation. So we saw the first interesting thing happens when mu is equal to 0. Something else happens to this equation, which is if mu is equal to epsilon j. If you set mu is equal to epsilon j, then what happens? Nj equal to infinity. There is a divergence. And this divergence is really the heart of, or is known as Bose-Einstein condensation. You can talk for weeks and weeks about this. I wouldn't be able to because I don't I don't think I quite understand it very well. I can see this where it comes from, but many of you probably already understand it or have read about it better than I have. But you can see what's going on here. It is due to this -1 thing that shows up over here. If by any chance we had a +1, this wouldn't have happened. So what's happening over here is that macroscopic number of particles all collapse into one state with energy equal to chemical potential. This is very strange. I will post you can actually go to Wikipedia, and there is a nice illustration of this on Wikipedia if you go to the Bose-Einstein condensation page. So check Wiki for this, where there is a nice GIF there showing how this actually happens. But mathematically, you can see what happened over here. If you set mu is equal to epsilon j, it's that energy level, which is not necessarily zero. You can imagine, okay, at zero temperature, everything condenses into ground state. So what's the big fuss? But here I'm talking about finite temperature. At any beta, if you had mu is equal to epsilon 3, everything would condense in this excited state, for example. That's pretty strange, right? And this has been realized in experiment. It was predicted way early. It has been realized in experiment, and a Nobel Prize has been given for it.
Can I ask a quick question on the mu equal to 0 statement?
Okay.
So here I can understand that we can arbitrarily add arbitrary numbers of photons or phonons, and that can be seen that can be interpreted as mu equal to 0. But other than that, is there any direct way of deriving the number, the value of mu here?
Well, we are doing grand canonical ensemble, right? So mu is a control variable. You cannot derive it. In the grand canonical ensemble, you can, mu is something you control. It's specified.
Okay, so if we switch to another ensemble,
you could try. I wrote down the formula for you. Good luck. You can try equation 9.
Okay. So you're saying the only way of arguing the mu equal to 0 is to either relate the Bose-Einstein distribution with the Planck's distribution.
Yeah.
Oh, okay.
It's not only way. It's one way. It's one intuitive way for me. Okay. And this Bose-Einstein and Fermi-Dirac is easy to derive using grand canonical. Using canonical, I'm not saying it's impossible. Maybe some books do it. I haven't seen many, but it's quite hard because of that restriction that everything must add up to n. Okay, great. Now let's do quickly Nj is equal for fermions also. For fermions, once again, that writing is terrible. For fermions, Nj will have the same formula, partial ln z by partial minus beta epsilon j. But now we are going to use equation number 12. And equation number 12 has a crucial difference. Equation number 12 has this plus over here, and the thing is not in the denominator. So the things are going to look a bit different. Use equation 12. And what you get over here is 1 over e to the power beta epsilon j minus mu plus 1. So average Nj for Fermi-Dirac is this. This is equation number 14. So let's compare 13 with 14. In the numerator, we have 1. In the denominator, we have e to the power something plus minus 1. In Bose-Einstein, we have a -1. In the Fermi-Dirac, we have a +1. So you can never have this divergence in Fermi-Dirac distribution. Even if you set epsilon j is equal to mu, you just recover half. And that is very interesting. For those of you who have done solid state physics, you realize basically you're saying equal 50% probability of being there if you recover half. And we will revisit this when we look at electrons, the heat capacity of electrons. So we can write down the full thing now as average Nj, Fermi-Dirac or Bose-Einstein, we can write in the same formula, is given as e to the power beta epsilon j minus mu plus minus 1. And this is quite important. And many of you, I am sure, especially those of you who do anything related to quantum mechanics in your research, if you ever deal with electrons or even classical mechanics, you will use this formula at some point or the other. You will come across papers using this formula. It's, I mean, the whole, the fact that we are talking right now, computer, electronics or everything really depends on this type of formula. It uses it in so many different ways. So it's a very important formula. And you can see FD does not show condensation, right? Because it has this +1 formula. So the Fermi-Dirac here leads to plus, and the Bose-Einstein leads to minus. Apart from that, everything is same. Any questions?
More like a comment, which is that I actually I was reading up on some stuff, research work and stuff. It turns out that there was a group that had shown that the FD condensate exists.
Oh, really?
So, yeah, maybe some interesting reading there for anyone who's interested.
You should post it on the Slack channel. Can you do that?
Sure. Yeah. Cool.
Good.
What are you talking about, Smritin? Like
he's saying that even Fermi-Dirac can condense.
Yeah. So the idea. I mean, so I believe what happened was like from the Bose-Einstein condensate group, like the student who was like the grad student then, eventually sort of went on to do like a Fermi-Dirac fermionic condensate, and then unfortunately passed away. Yeah, but yeah, that was yeah. She was apparently she was like one of the 222 like in the process of getting a Nobel, but then that happened. So apparently that didn't happen. So
okay. Yeah, I should put it on channel. I would like to read about it.
If you're talking about the BC to BCS transition, then I can understand. But here, I think what's written, you're talking about the condensation of Cooper pairs instead of pure fermions. But we can discuss later.
Yeah, please. I would love to see this discussion on Slack. Okay, so please do that there. Just not on direct message. Post it on channel. I would like to see what you're talking about and learn more. Okay, but the thing that I want to talk about next is what happens to quantum ideal gases as we approach high temperatures and low density. So you could even consider this as our application 4 evaluation. I'm not going to talk about much more about this. I will just talk a little bit. I will give you the expression that we are trying to look at. And then after spring break, next week is spring break. After spring break, we will look at it carefully. So we know in quantum mechanics is something that applies at low temperatures and higher densities. If you have only one particle in a system, then what's the point in talking about fermion or boson, right? It doesn't matter. The statistics just doesn't matter. Furthermore, if you go to very high temperatures, again, quantum mechanics stops to matter. And we know that from the de Broglie principle and things like that, right? In real life, I mean, when you tell someone, oh, I'm going to meet you for coffee, you don't have to talk about uncertainty principle or things like that, right? It's classical world and things like that. So we expect that at very high temperatures and low density, classical mechanics should be recovered. So if we have n indistinguishable particles, and this is where the distinguishability and indistinguishability comes in. If you have n indistinguishable particles, which are classical, in the same model, epsilon 1, epsilon 2, blah, 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 could we write down their partition function? How would it look like? And let's say indistinguishable and independent particles, right? So we would so since we have independent particles, we would calculate the partition function for one particle, Q1, right? Take it to the power n. How would this look like? This would look like, actually, I don't think I want to get into this right now. Let's do this after spring break. But this is the topic that you can think about, and we will start with this after spring break. There is no point in squeezing a new topic right before spring break. So it might, there is one homework. The reason why I'm tempted to do this is because there is one homework problem where if I do this, you will write the wrong answer, and then I get to cut some points. So maybe if I don't do it, you will write the right answer. So let's see how that turns out. I won't tell you which problem, but there is one problem where when I do this, a lot of people end up writing. So your hint for that problem here is and n tends to infinity. Anytime we talk about classical limit, we think about very, very large number of atoms, right? So this is what we will start after the break. Okay, any questions about all of this?
So this is just to clarify, the average Nj means the average number of particle on the jth energy level
Yeah.
with time, right? With time or ensemble. Yeah.
So because you have, let's
Yeah,
look at this, N1, N2, N3, Nj, and you
Yeah.
have, let's say 200 particles. So you
Uh-huh.
know that, again, here I'm plotting the canonical one. So I can talk about n. So I can talk about 200. So I know that if there are 50 of them in N1, 20 of them in N2, then I cannot have 140 of them in N3 because 140
Understood.
plus 50 plus 20 will be 200. So this is the value I'm trying to calculate.
Mhm.
Okay, great. So the homework is there. It's been there for a while. Work through it. It will be a bit challenging. It's really applying all these concepts. Sometimes students, when they take StatMech, they feel almost a bit of a disconnect into what we do in class and what we do in homework. It's like, wait, it is so different, but it shouldn't feel that way. And everything is open internet. It's because the idea is to learn. You will see similar problems solved. Take help from the internet and try to solve them properly. In the last homeworks, I saw many of you lost points. You could have gained almost full points by being just a bit more careful. So you have lots of time. Please be a bit more careful, and you can all get very, very good points in this homework. Okay, and then when we come back after spring break, we will talk about application 4. Otherwise, have a good spring break. Those of you who are going to APS meeting will probably be busy like me. And normally I would say I would have seen you in APS, but with Zoom APS, I don't know. I don't think I'm going to see any of you. Maybe I will. Okay, good. So take care, everyone, and see you after spring break.
Bye-bye.
Bye.